Okay, next we want to look at chapter 16, which is all about mixtures. So this is an important chapter to understand because most of the materials that we deal with in our world are actually mixtures. They're not often entirely pure substances. And so chemists need to understand how mixtures form and how to deal with them. And so we're going to talk about these things in this chapter. We're also going to talk about how chemists classify different kinds of matter. And we're going to talk about different types of mixtures. We're going to talk about solutions and also something that's similar to a solution called a suspension. We're going to talk about solubility, which refers to how things form solutions. We're also going to talk about soaps and detergents, which I've always found a really fascinating thing. How is it that soap works? We're going to learn that in this lecture, which is really cool. You may have heard of hard water and soft water. We're going to talk about what that is and how you can actually make hard water softer. We're going to talk about how water can be purified to make it drinkable. And we're also going to talk about wastewater treatment. So there's a lot to unpack in this chapter, so let's get started. Now, I said earlier that most materials are mixtures. So we want to talk about what does that mean for something to be a mixture. And so something that's not a mixture would be a pure substance. And a pure substance is a material consisting of only one type of element or compound. So if I have a bar of gold that only has gold atoms in it, that would be a pure substance, pure gold. If I have water that only has H2O and nothing else in it, that would be pure water, a chemical compound that's pure. But if I have a mixture, that's going to be a collection of two or more pure substances. And so you might think, for example, of if I take some sugar and I dump it into water, that sugar could dissolve in that water. And then I have a mixture of both water and sugar. Now, this is very, very different from a chemical bond. You know, it's not like when I have hydrogen and oxygen and I bring them together and form water, which is a completely different thing. When I form a mixture, the two different things retain their chemical properties. So, for example, if I take just some sugar, like powdered sugar in my hand, and I lick it, it's going to taste sweet because its chemical properties trigger sweetness in my sense of taste. But if I take that sugar and dissolve it in the water, I haven't turned the sugar into something else. I've just separated it physically so that it's dispersed among the water molecules. If I drink that water will also taste sweet because nothing is really changed in those sugar molecules. So that means that this kind of process is a physical change, not a chemical change. Remember, we talked about table salt, which is sodium, something that is very dangerous, and chlorine, which is very deadly. And you mix them together, sodium chloride is just table salt. It's completely different material. The sodium and the chlorine don't retain their chemical properties. When you form a chemical compound, you make something that's new. But with mixtures, you're just mixing them together. You're not changing them chemically. So we can see this illustrated here in this slide. You have, over on the left here, you have a bunch of packed together sugar molecules. And sugar, the official name of sugar is sucrose, and its chemical formula is C12H22O11. And here I have a spoon that has sugar, and it's, pure sugar, and I dump my pure sugar into coffee or into water or whatever. And so if I dump it into water, for example, I've got a bunch of water molecules surrounding a bunch of sugar molecules that have been separated from each other. They're floating around in the water. They're not packed together anymore, but they're still sugar molecules. And so that's what we're talking about when we're talking about a mixture. It's literally two or more pure substances that have been mixed together, but they haven't been chemically changed. Now let's look at how matter is classified by chemists. And of course, there are different kinds of way that matter is arranged, and so that means chemists have had to come up with different kinds of classifications. And this slide looks really complicated, and it kind of is, but we want to go through it because it's important. And this corresponds to a lot of text in your chapter in your textbook. So you definitely want to read through these sections in your textbook for a deeper understanding of what's in this slide, because there's really a lot here going on, and the descriptions in your textbooks will really help you understand it more deeply. So if you haven't been good about doing your reading assignments, make sure, especially in this chapter, that you actually read the chapter, because I think you'll find it very helpful. And of course, as always, if you have any questions, you can always shoot me an email or get in contact with me, and I'll do everything I can to help you out. But let's look at these different classifications now. So we've got matter, and we're talking about pretty much all of the kind of matter that we deal with here on Earth, and chemists will classify it with being either pure substance or an impure substance. And when we mean impure, that implies it's a mixture. And so we have a mixture, or we have a pure substance. So let's look at continuing on. If I'm considering the things that might be pure substances, we've really got two options here. They're elements. Those are the things on the periodic table. Gold. So I can have a bar that's pure gold. There's nothing mixed in the gold. It's just gold atoms. Sulfur. Nitrogen. These are all elements. I could list any of the elements on the periodic table and have a pure sample of them, and that would be a pure element. I could do the same thing with compounds. I could take salt, which we know is sodium chloride. If I have some salt and it's got nothing else mixed in it, there's no iodine mixed in with it, or there's no sugar that's spilled into it, it's just pure salt, that would be a pure compound. And so any chemical compound that you could name, carbon dioxide, ammonia, water, anything like that, you could have versions of it that were pure and versions of it that were mixed with something else. If you've got pure water, that's a pure compound. If you've got pure table salt, pure NaCl, that's a pure compound. So that's our first major classification, substances that are pure. Now, there's quite a lot more when we talk about substances that are impure, or rather substances that make up mixtures of pure things. So we're going to talk about mixtures, and there's two different kinds. And look at these words. These are really big words, and if you've never heard them pronounced before, you'd probably be inclined to mispronounce them. I hear people mispronounce them all the time, but it's not that hard. So one kind of impure mixture is called a homogeneous mixture, and that's how you say that, homogeneous. So we can talk about what that is in a second, but I want you to understand how to say it, homogeneous mixture. And then over here we have the other kind, heterogeneous. And so we have homogeneous and heterogeneous. And let's talk about what that means. So let's talk about what these mean. We can talk about a homogeneous mixture, and that is a mixture that is uniform. It's been mixed up so well that it's completely uniform. In other words, if I take a sample from one place and a sample from another place, it would have the same constituent parts in the same ratios. Let me give an example. So one of the items here listed as a homogeneous mixture is air. And that's just like the air we breathe every day, the atmosphere of planet Earth. And there are a few other things mixed into it, but mostly it's nitrogen and oxygen. So consider the room that you're in right now. The room that you're in right now is filled with air. And that air consists of about 78% nitrogen and about 21% oxygen. And the rest other stuff. But mostly the air that you breathe is 78% nitrogen and 21% oxygen. So what that means, it's a homogeneous mixture. If you take a sample of the air close to the ceiling, it's going to have 78% nitrogen and 21% oxygen. If you take a sample of the air near the floor, it's going to have those same percentages of nitrogen and oxygen, because the air has been so well mixed together that everywhere in the world it's the same percentages. It's all samples of air roughly contain those ratios of nitrogen to oxygen. Or Another example, white gold, which is a combination of gold, which has a symbol AU. We've talked about that previously. And palladium, which has a symbol PD, chemical symbol PD. And so if you have white gold, it's going to be a certain percentage of gold and a certain percentage of palladium mixed together. If you have a ring that's made out of white gold and you cut it in half, one half of the ring is going to have the same percentage of gold and the same percentage of palladium as the other. They're purely mixed together. That's a homogeneous mixture. And the other possible kind of mixture that you can have is a heterogeneous mixture. And we can see up here some examples of heterogeneous mixtures. Here we have sand and water, oil and water, sand and salt. If I have a glass of water and I take a handful of sand, dump it in the water, that sand is just going to sink to the bottom. And what we're going to find is if I take a sample of that mixture of sand and water, if I take a sample near the top of the water and one near the bottom of the water, the sample in the bottom of the water is going to have a lot more sand in it than the one at the top. And even if I shake it up, I could shake it up really good so that there's sand dispersed all through the water. It's not going to be uniform. If I took a sample in one portion of the beaker or the container of water and a sample in another portion of the container, I'm not going to get exactly the same amount of sand compared to the same amount of water. So I'm hoping that makes sense. If not, don't freak out, because we're going to look at some examples in another slide, and I think that'll bring it home and make it really clear, even if it's a little bit nebulous still. But those are the two main ideas. So here I've listed the distinction. We can talk about homogeneous mixtures, and they're mixtures that have the same composition throughout the mixture, and heterogeneous mixtures, they have components that can be seen as individual substances still. So they don't get so thoroughly mixed up that you can't tell them apart anymore. If I mix sand and water, I can see the sand in the water and it still looks like sand. But if I have white gold, I don't see like little spots of gold and little spots of palladium. I just see it all mixed together. And so that's the distinction between a homogeneous mixture and a heterogeneous mixture. Now there's one more classification, because when we're talking about homogeneous mixtures, there's actually two kinds. All the kind I've talked about so far are listed under this heading of being a solution. So in a solution, all the components are in the same phase. So air, for example, is a mixture of nitrogen and oxygen, and they're both in the gaseous phase. They're both gases. White gold is made out of gold and palladium, and they're both solids. They're mixed together, but they're both solids. They're both in the same phase. And so that's what we call a solution, is when the things that are mixed together are all in the same phase. The other thing that we can talk about is a suspension. And when you have a suspension, it's a mixture of things that are in different phases. So, for example, milk is a suspension. It's a mixture of water, which is a liquid, with solid proteins and solid fats. And so you have a bunch of solid particles that are suspended in the water, but they're mixed up so thoroughly that it's basically a uniform substance. And so there are other examples of suspensions that you're familiar with. Of course, blood. Everyone's experienced blood at some point in their life. It's a suspension involving water with solid proteins that are mixed up in it. And fog is another example where you have air that has tiny water droplets suspended in it. So this is the difference between a suspension and a solution. So just to recap everything, pure materials consist of a single element or a single compound. Impure materials consist of two or more elements or compounds that are mixed together, and those mixtures may be either heterogeneous or homogeneous. And recapping what we mean, in a heterogeneous mixture, the different components can be seen as individual substances. In a homogeneous mixture, the composition is the same throughout. So here we have some different examples. Granite is a heterogeneous mixture. All the ones up top here are the heterogeneous mixtures examples. And so if I take a little chunk of granite here and a little chunk of granite there, you can see that there's different colorations of the different constituents of the granite. So it's not uniform. That's a heterogeneous mixture. Same as like snow in a snow globe. If I shake the snow globe up, there's snow particles dispersed, or quote unquote snow particles dispersed. But if I took a little sample near the top and a little sample near the bottom, it's not gonna, if I counted, I wouldn't count the same number of snow particles in a sample up top and a sample in the bottom. Another example of a heterogeneous mixture is a pizza. You can see the different constituents spread out. It's not uniform. Whereas the homogeneous mixtures listed here, we have air, which if I take a sample of the air here and a sample of the air there, it's pretty much going to be the same. Clear seawater, white gold, we've talked about these as homogeneous mixtures. If you take a sample in one place and a sample in another place, it's going to look exactly the same. It's going to have the same ratios of constituent parts. It's basically the same stuff. And then, of course, when we're talking about homogeneous mixtures, we have two subcategories: solutions, where all the components are in the same phase, and suspensions, where different components are in different phases. So here's an example. Let's check our understanding. Is the air in your house a homogeneous mixture or a heterogeneous mixture? And our options are A, it's homogeneous because it's mixed very well. B, it's heterogeneous because of the dust particles it contains. C, it's homogeneous because it's all at the same temperature. Or D, it's heterogeneous because it consists of different types of molecules. Well, we can eliminate D pretty quickly because that's not the key thing that determines whether it is homogeneous or heterogeneous. And we can eliminate C because it doesn't matter whether things are at the same temperature or not. So it's either going to be A or B. And you might be inclined to say homogeneous is mixed very well. And I've already told you that air is homogeneous, but you can make an argument either way, because if your house is anything like mine, if you've ever looked at sun shining through the window, you can see little particles of dust floating through the air. And so that would mean that because of these dust particles, you're going to end up with a heterogeneous mixture. So the answer would be B. Next, we want to talk about solutions in more detail. Now, remember, a solution is a homogeneous mixture consisting of ions or molecules. Now, when you have a solution, that means one thing is dissolved into another thing. And so the solvent is the major component of the solution, and the solute is the minor component of the solution. What does that mean? Well, imagine you had a liter of water and you dissolved a teaspoon of sugar in it. There's a lot more water than there is sugar. So the water would be the major component, and that would be the solvent. And the solute would be the minor component, so that would be the sugar. The solute is the stuff that gets dissolved, and the solvent is what the solute gets dissolved into. Now, there's an interesting thing. If you, for example, take a liter of water and you've got a bunch of sugar and you just start spooning the sugar in, the sugar will dissolve and dissolve and dissolve, but eventually you get to a point where as you dump more sugar in, the sugar stops dissolving and it'll just sink to the bottom. And so essentially you've dissolved all the sugar that you can possibly dissolve into that water, and any sugar that you add to it can no longer be dissolved and it'll just sink to the bottom. At that point, we have what we call a saturated solution. It's saturated. You can't add any more solute to it. No more will dissolve. The next concept that we want to talk about is called concentration. Imagine you had some acid and some water and you mix them together. And in one case, you had a liter of water with a teaspoon of acid mixed in it, and in the other case, you had a liter of acid with a teaspoon of water mixed in it. Which of those two containers would you rather be dumped on you? Well, maybe not either, but I'd certainly prefer the one that had more water and just a little bit of acid than the one that was mostly acid with just a little bit of water. So what we're talking about here is the idea of concentration. And so there's an official way to define how concentrated something is. And so what you do is you take the amount of solute, that's the thing being dissolved, and you divide it by the amount of solution. And that would be the total amount of solution, both the solute and the solvent added together. So the total amount of stuff that you have, you divide the amount that's dissolved into the total amount. So we have our full definition. The concentration is a measure of the amount of solute dissolved in a solution. And one of the things that we find is that we end up in chemistry very often talking about very, very large numbers. And so one of the ways that we can characterize them is in terms of how many moles there are. A mole is just a super large number. It's actually 6.02 times 10 to the 23. If you write this out in normal numbers, that would be 602 with 21 zeros after it. That's a really, really long number, really, really big number. And this is a number that shows up very often, and it's related to the periodic table. But basically, it's just a number. What's a dozen? You probably all know that a dozen is 12. And so if I say the word dozen, you know that means 12. What's a couple? If I say I've got a couple of friends coming to dinner, how many friends do I have coming to dinner? You all know that I have 2 friends coming to dinner. The word couple means 2, the word dozen means 12, and the word mole means 6.02 times 10 to the 23rd, which is that really gigantic number that shows up in chemistry a lot. Now, what's interesting is that the formula mass of a substance expressed in grams contains 1 mole of that substance. Now, if we look up carbon on the periodic table, we can see that its atomic mass is 12. That means 12 grams of carbon contain 6.02 times 10 to the 23rd carbon atoms. Oxygen has an atomic mass of 16, but when you form oxygen, it joins together into the O2 molecules, and I apologize, these formatting of these chemical formulas has gotten a little bit mixed up on my PowerPoint. That 2 should be a subscript. That all these numbers should be subscripts, like this should be O2. I'm not going to rewrite all of them, but that's basically an error in formatting there. I do apologize for that. In any case, we know carbon dioxide, if you add up the masses of the carbon and the 2 oxygens, it has a mass unit of 44. And so that means that 44 grams of carbon dioxide contain 1 mole of carbon dioxide molecules. Now, the reason that we're talking about moles is because they're very useful for expressing things like concentrations. And so if I have a liter of water and I have a mole of sucrose, that's of course table sugar, then I have a concentration of 1 mole of sugar per liter of solution. And so 1 mole of sucrose is equal to 342 grams of sucrose, and of course that gives us 1 mole of sucrose. Here we have water, which has the formula H2O, of course. It has a formula mass of 18. So how many moles of water are there in 18 grams of water? Well, the formula mass is 18, so 18 grams contains 1 mole. And therefore, that is our answer. Okay, so the next thing that we want to ask is how many grams of water are there in 2 moles of water? Now we know that there are 18 grams per mole, so if there are 2 moles, the answer is going to be 36 grams. Now, when chemists describe concentration this way, they use a term called molarity. And molarity is a unit of concentration expressed in moles of solute per liter of solution. So moles of solute, remember, solute is the thing that's dissolved, and solution is the total, both the thing dissolved and the thing you're dissolving it into. So that makes up the whole solution. So we have moles of solute divided by liters of solution. That's the molarity of the concentration. So there's also another very commonly used way of describing concentration. Now we've seen molarity. Another very common way of describing concentration is to use ppm, and that actually stands for parts per million. And it's a unit of concentration in milligrams solute per liters of solution. So 1 ppm means there's 1 part of solute per 1 million parts of solution. But you can actually find out that that's equivalent to 1 milligram per solute divided by 1 liter of solution. And so this is basically how you would calculate it. You know, how many milligrams of solute do you have per liter of solution? But that will also tell you how many parts of solute you have compared to 1 million parts of the solution. And so again, ppm, that stands for parts per million. Now, one of the things that we can talk about is how easily it is for one thing to dissolve into another thing. And so the term that chemists use to describe that is solubility. And solubility is the ability of a solute to dissolve in a solvent. So some things, like for example, sugar very easily dissolves in water. It has a high solubility. That's its ability to be dissolved. Oxygen, on the other hand, has a very low solubility in water. Oxygen doesn't dissolve in water very easily. Now, some oxygen can be dissolved in water, but not a lot. And so we would say that oxygen has a very low solubility in water, or even that it's insoluble, which would be another way of saying the same thing. But if we say something is soluble, that means that something can be very easily dissolved. If it's insoluble, it's not very easily or not at all able to be dissolved. And by the way, just because something can dissolve in water doesn't mean that it would dissolve in other liquids the same way. So it's possible that something could very easily dissolve in water, but perhaps maybe would not dissolve in oil or some other liquid. Now there's one other idea that's quite useful, and it's the concept of a precipitate. You've probably heard the phrase, if you're not part of the solution, you're part of the problem. Well, there's a kind of an old chemistry joke on that. If you're not part of the solution, you must be a precipitate, because the precipitate is a solute that comes out of the solution. And it's a kind of a weird process that happens. I told you in an earlier slide that, for example, if I'm dissolving sugar in water, I reach a point where I can't dissolve any more sugar in that water. It's completely saturated. But what's interesting is that the amount of sugar that you can dissolve in a cup of water also depends not only on how much water you have, but how hot the water is. When the water is very, very hot, its atoms and molecules are jiggling back and forth much, much faster, and so they're able to dissolve more sugar because they're whacking into the sugar harder and faster, and they're able to separate it and dissolve it. Now, if I have water that's at 100 degrees Celsius, that's up to the boiling point, so it's as hot as you can make water under normal conditions before it turns into steam, and I start adding in sugar, I'll dissolve the maximum amount of sugar possible to dissolve in liquid water under normal conditions. But then if I take my water off the stove and let it cool down, what I find is that sugar will remain dissolved, or at least it can remain dissolved, but if I disturb that water in any way, if I put something in the water or if I bump the water, what can happen is that extra sugar will come out, because water at 100 degrees can hold a lot more sugar than water at 20 degrees. So if I saturate the water at 100 degrees and then let it cool down, the water is holding a lot more sugar than it could normally dissolve. And if you create a situation where there's some disturbance in the water, that extra sugar will just undissolve. And that water that loses that extra sugar is called the precipitate. And so the precipitate is the part of the solute that comes out of the solution. And by the way, this is actually what would be considered, this is not in your textbook, it's just a little bit of extra information. This is what you call a supersaturated solution. When the water contains more sugar or whatever than it normally could because you've cooled it down, it's not just saturated, it's supersaturated. And so if I add just a little bit of extra sugar, that would disturb the water and it would provide an ability for the solute to form around it and come out. Now there is an interesting thing, because solids tend to become more easily dissolved when the temperature of the liquid you're dissolving it into is higher. But for gases, it's opposite. So if I've got oxygen dissolved in water and I heat it up, those atoms that are jiggling back and forth, molecules jiggling back and forth faster and faster, they're walloping those gas molecules and knocking them out of the solution. So gases tend to be less dissolvable when the temperature is higher, and solids tend to be more dissolvable when the temperature is higher. So let's do a quick example, check our understanding. Question: the amount of oxygen, O2, dissolved in the waters of the Arctic Ocean is greater than, about equal to, or less than the amount of oxygen dissolved in the warm tropical waters. Well, we just saw that when the waters are warm, it holds less gas, so we would expect it to be A. The answer is greater than. So last question here. Water by mass is 88.88% oxygen, almost 89% oxygen. You know, there's 2 hydrogen atoms, which are very low in mass, and then 1 oxygen atom, which is very big in mass. Why can't we breathe water if there's so much oxygen in the water molecules? And of course, we know the answer is because water is a different chemical compound than oxygen. H2O is very different from O2. And as we know, when elements form into chemical compounds, it completely changes their properties. Now, what's interesting, a lot of people think that fish breathe water, but that's actually not true. I told you in a previous slide that water does not dissolve oxygen very well. In other words, oxygen doesn't very easily dissolve into water, but a little bit does. And when you go into the oceans and lakes, you will find that dissolved in the water is some amount of oxygen. And that's actually what fish breathe. They breathe the oxygen, not that's bound up in the H2O molecules. They breathe the O2 that's dissolved in the water itself, and their gills act as filters that filter that out and enable them to separate the oxygen that's dissolved in the water from the water itself. And this is already a pretty long video, so I think we'll end it here and continue our investigation of this chapter in the next video.